Hello everyone. Today we're going to solve word ladder 2 problem. So let's understand the problem statement. Given two words, begin word and end word, and a dictionary's word list, find all shortest transformation sequences from begin word to end word. So we just have to transform from begin word to end word like this, right? So hit to hot. Right? In this example, these are the minimum length sequences, shortest sequences to reach from begin word to end word. Okay, so as you can see that from the begin word, we have to reach the end word by using this word list. So we just have to change one character from the begin word and then match, okay, this is a neighbor of that, so that, just one character difference here. So we just have to pick up this word as a next word, like hit will be transformed into hot, and we can just transform either to lot or a dot. Likewise, we can just form any paths. Okay, so we just have to return the minimum path sequences. There are steps involved to solve this problem. First, we need a data structure to represent, the word and its transformed neighbors. So the word can contain any transformed word which is available in the word list as its neighbor. Okay, so we just have to have a data structure which looks more or less like a graph so that we can perform traversals on it. Next, we have to calculate or assign distance of each node from the start node. Okay, so we are going to use BFS method to assign distance of each node from the start node. Please pay attention till the end of this video so that you will be sure what is actually going on. Next, we are going to construct all the paths, okay, from the start node till we reach the end node. Okay, so what are the various paths? So if we reach a node, so we can just explore all its neighbors. So go deeper until we reach the end node. So we have to form a chain. We have to keep track of the words in that chain. Okay, so this can be achieved using DFS. So please pay attention to that. And we just have to return. So if we construct all the paths, we just collect all the paths in the array. So if we found the minimum length, so we just have to calculate the minimum length as well, right? So while constructing a path, we just have to calculate its length also. So we keep track of its length for the minimum possible length. We just have to filter out. So we just have to ignore all the paths we constructed, except for the sequences, which is of same length, that is the minimum length. Okay. So let's see how we solve this problem. I would request you to please pay attention till the end of this video to get the full internal details how this problem can be solved. Okay, and please don't forget to subscribe. So we are going to implement all the steps here. So let's start. Okay, so the steps are first, construct a graph with the nodes, and then we have to assign distance for each node from start node, and what we are going to do is, yes, construct all the paths, return only min sequences. Okay, so in order to construct a graph, maybe we can just define a node here, structure of the node here. So I'll define class node constructor, which accepts a value, start value equal to val. We can just store the references of neighbors in this array. Distance. So each node must have a distance. So initially it will be -1, right? Okay, so let's start. So before starting all these steps, we just have to follow some preconditions. If the word list does not include the end word, all right, because there is no end word in the word list, then just return empty, right? We cannot solve this. So let's create return type. So answer equal to the array, and we're going to return that answer. Let's create a map so that we can just enable faster lookup. So whenever we generate a new transformed word from one word, we just have to look up, okay, this word is available in the word list or not, right? So we create a map and store all the items in the map, and see word list. dot for each word, then if, okay, just say if map dot set word true. All right, we have to make sure if the map does not have begin word, we have to make sure that it has. So we include that in the beginning. So map dot set begin word true and word list dot unshift, because we are just inserting in the beginning of the array. So unshift begin word, right? And we are going to construct a graph here. So let graph equal to new map. Okay, we're going to have a hash table kind of structure to maintain this. So for example, this is hit. It will have a new node. For example, this is a node. Okay, node has hit and a neighbor list and the distance. So this is a key, and this is going to be the value. Okay, the value will contain one node and its neighbor. A node has its neighbor, right? So neighbors array should contain the references of real node, not the word. Okay, so we'll construct that. So for let word of word list, uh, if the graph does not have, so if the graph does not have that word, then create new graph dot set word new node, okay, of that word. So we just have created a new graph node of that word, and we just have to create all its neighbors, right? So here we want the neighbors list to be added to the graph. So we'll just create a function to generate all its neighbor. We call it as function get neighbors. Get neighbors. We just have the lookup word list, because when we generate a new word, we just have to look up whether this word is available in the word list or not. Okay, return or let neighbor equal to the array. We just have to return. We just have to generate a substring by changing one character. So we have to traverse for each. So let I equal to 0 and word dot length I plus plus, and let adjacent word equal to word dot slice from 0 to that particular index plus some character here, and word dot slice from I plus 1. So whatever the index plus 1. So we skip just one character of that of in that index. So we just have to generate a new character, like, all the lowercase alphabets. So create one loop here. Let the character from all the small lowercase alphabets. So I'm going to replace this here. So we have generated one adjacent word here, the transformed word. Let's call it as neighbor word. And if that map has the neighbor word, and also the current word must not be equal to that neighbor word. So it's very highly possible that we generate the same word, right? For hit word, this could be H and this could be T when we reach the character I. So this could be the same word. Okay, so we should not add the same word to the neighbors list. So push neighbor word. Okay, so we just have to return that. So after creating the main word in the graph, we just have to get all the neighbors. So and then add it to the graph. So for let neighbors ng, I'll call it as ng of get neighbors. Given that map, we have that map of words and then word. Okay. Let's try to get the existing node in the graph, because no need to recreate it every time, right? So if it has already been created, we have to get the existing node here. So let node equal to graph dot get ng. Okay, if there is no such node, then we have to create a node of that word and add it to the graph. Okay, and after creating the neighbor node, we just have to graph.get that word actual parent. So this is the current word, right? So current word dot neighbors dot push the neighbor node. Got it? So we just constructed like this. Created hit, and we got hit and new node that is hot and empty -1 and -1. So like this, right? So for hit there is only one neighbor that is hot. So just for the first iteration, we just created like this. All right. So let's say the distance is 0 currently. Okay. So for the current node, or let's say -1 because we are going to increment that. So we are going to perform the BFS traversal here, right? So in order to perform BFS traversal, we need to have a processing list, as I mentioned in the word ladder 1. So let's say Q. So this Q is the processing list for us now. So initially that Q will have the begin word. Okay. So while Q is not empty, so what we are going to do is, so we are going to process all the nodes in the current queue. Okay, the current queue will be one level, right? So we have the begin word in one level, so which is the current level, and if we explore all its neighbors, that will be the level 2, right? So we'll be appending all its neighbor to the processing list, right? That's the next level of the list. So let's pop all the nodes from the processing list and assign the distance. So the current queue can represent the list of nodes which is of the same level, right? So we're going to pop everything out of it and then assign the distance. So uh, let size equal to queue dot length, and till the size we are going to pop every item in the queue, so and assign the distance. So let current node equal to queue dot shift. We are taking the first element out, and if the current node dot distance is not equal to -1, which means this node already having the distance assigned. We don't want to assign a new distance for that. So let's skip that if it is already having. If not, then say distance equal to current distance, current distance plus 1, right? And we have to get all its neighbor. So for like neighbor of current node dot neighbors, if again we have to perform the check because it, so this neighbor could be having the distance already assigned by some other node. So if n dot distance not equal to -1, so or n dot distance is equal to -1, then q dot push that neighbor. All right. So let me summarize the step 2 here. So we have the distance -1 initially, and we have the processing list, which contains the initial node. So we can see that this processing list at the time will be containing the nodes which is of same level. All right. So we are just giving first node and then assigning the distance. And then for each of its neighbor, just if there is no distance assigned, then we're just adding to the current processing list. Since we are restricted to the size, we can just, you know, take only the nodes which is of the same level. All right. So after this step, we'll be having the distance assigned. We have to construct the paths. So for constructing a path, we have to follow depth first search method, and also we have to trace the word list along the path, right, for each path. So let's have a stack here because we're going to explore deep, right? For each neighbor we add. So the least neighbor, and we have to trace that to reach the end word. So let's say we have minimum, which is of a big number, maybe infinity. Okay. And we have a stack here. Stack initially contains graph of begin word. So while the stack is not empty, greater than 0, let current node equal to stack dot pop. So we'll check the current node is equals to the end word. If it is the end word, we have reached the end word, right? So we have to update the minimum, and as well as we have to update the sequence, right? So we have to keep track the sequence here. If we reach the end word, we have to add that sequence to the answers list. So what we can do is, along with the node in the stack, so we can also have a chain. Okay, we can also have a chain. So this is one node in the stack, right? This is one item in the stack, and which consists of begin word node and also the chain. Okay, so we are going to maintain the list of words here. So along the path till we reach the end word. So if if so, we call that as chain. Okay, so we pop the current node and the chain. Okay, so if we reach the end word, then we can update the minimum. So math.min, whatever minimum, plus chain.length plus 1. Because we are going to add this current node to the chain, right? So if we reach the end word, then this node is also going to be added to the chain. All right. So answer.push, whatever the chain items, plus current node.val. So if it is not the case, else, if that is not the end word, what we're going to do here is, so this part is very important because we can explore all its neighbors. We can explore all its neighbors and we can just have it in our path. We should be selecting the neighbors which is of the next level, right? As you can see in this example, there are a lot of solutions, you know. So from start word to end word, and this is a solution which includes all the nodes, right? And also this. So if you closely notice that this is the initial level, so hit, that's of distance 0 here. Then we are exploring to the next, which is this is the only neighbor, and we are selecting here. And from hot, we are selecting the next neighbor. And if you closely notice that from lot, we are selecting a neighbor which is of the same level. So also there could be chances that lot can also go to hot, right? So lot will have the neighbor hot and dot and also log. So we have to choose the neighbors wisely such that we reach the end node very quickly. If you are in this node, we can select all these neighbors to travel, right? But if we choose this, we'll fall in a cycle, right? Then again, hot will go to lot and lot will go to, this is a cycle then. So in order to avoid this, so we're just having a condition that we are going to select a neighbor which is of next level. Okay, we are not going to select the neighbor which is behind us, and we are not going to select the neighbor which is with us, but we are going to select a neighbor which is ahead of us. So that's the reason we have just created distance from start node to end node. Okay, so we are going to apply this condition in that traverser. So we are going to get all the neighbors. Let neighbors of current node dot neighbors if the neighbor dot distance is greater than the current node's distance, right? Because by selecting this neighbor, we'll be sure that we'll be reaching the end node as soon as possible. So if a neighbor is ahead of us, then we can just have to push a stack item that contains the neighbor node, which is the next node we are going to traverse, and the chain, which includes the parent node, right? So, yeah, so whenever we reach, we have the answer here, and also we are also having the minimum tracked here. So the fourth step is we have to return only the minimum sequences, right? So answer will have all the paths. Okay, we just have to select only the minimum sequences here. So answer equal to answer dot filter for each array in that answer. So the length must be equal to the minimum. All right. So if the length is of minimum, then select that array. Okay. So finally, we are going to return the answer. So the preconditions here, and we have constructed the graph, and we assign distance of each node from start. So in order to avoid the cycle, also to avoid the unnecessary paths, and we are constructing all the paths whenever. So initially we have the begin where we started from the begin word and the chain empty chain. Whenever we reach the end word, we just popping out that current node in the chain. So the current node is the end node, and we calculate the minimum, and we just have to append the current node value to the chain and push the whole chain to the answers list. And if that is not the end word, we still have to continue with the neighbors. So we select any neighbor which lies ahead of us from the start node. So we just have to select that node and then push it to the stack to explore, to construct the path. So, okay, so we are filtering out all the paths and then getting only the minimum. Okay, so let's test this. Something wrong. Okay, nothing is there. Okay. Okay. So let's print our graph and check. So log graph. So distance is 0. Hot. The distance is 0. Oh, okay. Oh, okay. So we made a mistake here because whenever we try to assign the distance for after we pop out everything, after we dequeue all the nodes in the current processing list, so we just have to increase the distance, right? So let's print the graph again. Let's check. Okay, so let's check the distance. Yeah, hit has the distance of 0, correct. Hot has a distance of 1, yes. And dot has a distance of 2, and lot has a distance of 2, yes, correct. And cog, yeah, it's the last word, right? So it has a distance of 4, and log has distance of 3, and also there could be another lot. Okay, sure, yeah. So dog and log is of 3. The distance is 2, yeah, correct. So let's submit this with this. Yes, sure. Hope you enjoyed this video. Please subscribe for more videos like this. And thanks for watching.